Okay, so that's rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. Okay, factor out the common factor, that's rho squared sine squared phi, and in parentheses I have cosine squared theta plus sine squared theta. Okay, and that's 1. So this is just rho squared sine squared phi. Okay. So this is always a good idea to just somehow engrave it, remember it somehow, okay? It's gonna save you a lot of time. Similarly, x squared plus y squared plus z squared is equal to, well, that's x squared plus y squared that we just figure out how much it is in spherical, rho squared sine squared phi plus z squared, and z in spherical coordinate is rho times cosine phi, because it's squared. But now this is rho squared sine squared phi plus cosine squared phi, and sine squared plus cosine squared is 1, so that's only rho squared. Now, again, this is something that you want to remember. Okay, or for example, when you're doing the test, you want to have this on the side so you can always refer to it. Okay, now let's go back to the example that I just did, to this example right here, right? Rho is equal to c, rho is equal to c, right? Not phi, rho is equal to c. Okay, but from here, right, how much is rho? Rho is equal to square root of x squared plus y squared plus z squared, right? So this implies this is square root of x squared plus y squared plus z squared, okay, is equal to c, or that's x squared plus y squared plus z squared is equal to c squared. And this indeed is a equation of a sphere centered at the origin with radius c, right? Exactly what we had here. So it's a sphere with radius c, right, centered at the origin. Okay, so this is the first change from that we have seen in this class, changing from spherical to Cartesian coordinates. Okay, so now let us look at the triple integral. Okay, so I want to change the integral over the solid E, or the three-dimensional region E, of f of x, y, z dv, or that's dx, dy, dz. What did I say last class? When we change this variables, this is going to be over some, let's say, region D, okay? And I have a function here of rho phi theta times the determinant of the Jacobian, right? And then let's say dw. So the question is, what is the Jacobian of what is the determinant of this Jacobian matrix? So the Jacobian is just the matrix consisted of the partial derivatives, partial x, partial rho, partial x, partial phi, partial x, partial theta, partial y, partial rho, partial y, partial phi, partial y, partial theta, partial z, partial rho, partial z, partial phi, partial y, z, partial theta. And now find the determinant of this, right? That's equal to the determinant of Now you can have your x, y, and z in front of you. Okay, so I'm looking for the partial derivatives. I have them in front of me, so I just evaluate them. Partial x partial rho is sine phi cosine theta. Partial x partial phi is rho cosine phi cosine theta. And partial x partial theta is a negative rho sine phi sine theta. Okay, now partial phi partial rho is just sine phi sine theta. Partial y partial phi is rho cosine phi sine theta. And partial phi partial theta, partial y partial theta is rho sine phi cosine theta. And the last one, partial z partial rho, is just cosine phi. Partial z partial phi is negative rho sine phi. And then z is not defined, is independent of theta, so this is just going to be 0. It makes sense to use what is called cofactor expansion along the last row, along the row 3, because it involves the 0, right? So the determinant is going to be cosine of phi times the determinant of this submatrix, right? Cosine of phi times the determinant of this submatrix. And the determinant of that submatrix is just, here I can multiply this term by this term, and that's rho squared cosine squared theta, cosine theta, and then you have sine phi cosine phi minus this product right here. But this product is already negative, so minus and minus becomes plus rho squared sine squared theta sine phi cosine phi. Okay? Minus, so it was this term times the determinant of this submatrix minus this term, but minus and minus becomes plus rho sine phi times the determinant of the submatrix consisted of these terms, right? So that's rho sine squared phi cosine
Rho
squared.
isn't squared, by the way.
Rho is not squared, thank you. Minus this times this, and this is already minus negative, so minus them minus is plus rho sine squared phi sine squared theta. Okay, so let's simplify this very big expression. How I'm going to simplify it? By factoring stuff. So this is cosine phi. Here I can factor these two terms, right? So that's rho squared sine phi cosine phi times cosine squared theta plus sine squared theta, plus here I can factor these two terms. So factoring them out and multiplying by this, I get rho squared sine cubed phi. In parentheses, I get cosine squared theta plus sine squared theta, okay? And now I move on because these are just one, right? Just one. So here we're left with rho squared sine phi cosine squared phi plus rho squared sine cubed phi. The common factor is rho squared sine phi, and in parentheses, I get cosine squared phi plus sine squared phi. Again, this is 1. So the Jacobian of the triple integral in spherical coordinates is rho squared sine phi, which means that whenever we are evaluating an integral in triple integral in spherical coordinates, okay, that's going to be, let's say that phi goes from gamma to xi, okay, theta goes from alpha to beta, and rho goes from a to b, okay. We have a function of rho theta phi times the Jacobian rho squared sine of phi d rho d theta d phi. Sorry, that's d phi at the end. Okay. So the thing that you have to know is this guy right here. Okay, whenever you're flipping, changing to spherical coordinates, don't forget to multiply your integrand by this term right here. Okay, let's do example 1. Very simple introductory example. This example could have been done in spherical, in just one. The introductory problem for triple integrals. So that's rho squared sine of phi d rho d phi d theta, and then rho goes from 0 to 1, phi goes from 0 to pi over 2, theta goes from 0 to 2 pi. Okay, obviously you can see that d rho doesn't depend on phi and theta. Phi doesn't depend on theta. Theta, they're all independent, so this can be written as from 0 to 2 pi d theta times the integral from 0 to pi over 2 sine phi d phi times the integral from 0 to 1 rho squared d rho. And now this is simple. This is 2 pi times negative cosine of phi, where phi goes from 0 to pi over 2, times 1/3 rho cubed, where rho goes from 0 to 1. And that's equal to 2 pi negative cosine of pi over 2 is 0, minus cosine of 0 is 1, times 1/3 1 minus 0. This is 1, obviously 1, so the answer is 2 pi over 3. Any questions? Okay, if there are no questions, then just recall that when you're looking for a volume of a solid, right, you have to evaluate the triple integral of 1 d w over some region E, okay, of 1 in Cartesian coordinates. But if we're talking about spherical coordinates, then here you have d rho, d phi, d theta, okay, depending here on how this all on the bounds of rho, phi, and theta, right? Of 1, but be careful, times the Jacobian, don't forget the Jacobian, rho squared sine phi. Okay, that being said, let's set up as an exercise, set up the integral set up the triple integral for the volume of the region bounded by z is equal to square root of 3 x squared plus y squared, and the hemisphere z is equal to square root of 4 minus x squared minus y squared. So how are we going to, what are these? Can you guys recognize what is this? And what is this? As solids, right? Can you recognize them?
Do you want us to answer?
Yeah.
Oh, okay. Well, the first one, I think it's a cone. And the second one looks like well, the upper half of a sphere, and the first one is the first half of this
hemisphere, right?
Yeah.
Right. So this is if you have z squared plus x squared plus y squared, that's equal to 4. That's the sphere, right? But because z only takes on positive values, positive square root of 4 minus x squared minus y squared, then I get just the hemisphere, right? Okay. With radius 2. Okay. And then I have this cone here. Okay. So for the volume, they're bounded by. So what is the volume bounded? What is the solid bounded by these two solids? Okay, so that's like an ice cream cone that we already have talked about. It's like this. It's like that. When we are talking about setting up the volume, all the volume is going to be equal to the triple integral of course, in spherical coordinates, rho squared sine of phi d rho d phi d theta. So basically, we have to find the bounds of theta phi and rho. Okay, well, this is an easy problem. This problem is easy problem because the bounds are easy. First of all, look at theta. This solid revolves around the z-axis for 2 pi, right? So theta is between 0 and 2 pi. Now, the radius rho. This distance from here to here, this is where the cone meets the hemisphere, right? So this also has to be, this point is on the sphere also, on the hemisphere also. So it's 2. And then it continues. The radius rho is always 2. So rho is bounded between 0 and 2. And the last one that you have to answer, well, that is going to be how much is phi bounded by? Well, phi starts from here, right? From here, and it goes all the way to here. So that means that phi starts from 0, and the only tricky part here is what is the upper bound? What is the upper bound of phi? Okay. Now, in order to answer that, we have to find this point where these two equations meet. Okay. There are different ways of how to deal with this. One way to do it is to look at the cone here, right? Because this is where the cone meets the sphere. So one way to do this is to find the intersection between these two solids. So that's because z is equal to z on this ring here, on this circle here, right? So that's z is equal to square root of 3 square root of x squared plus y squared is equal to square root of 4 minus x squared plus y squared. Okay. Now x squared plus y squared in spherical coordinates, that's what I told you. It comes back over and over. X squared plus phi squared in spherical coordinates is rho squared sine squared phi. So this is equal to square root of 3 square root of rho squared sine squared phi, which is equal to square root of 4 minus x squared plus y squared, rho squared sine squared phi. Okay, so this is square root of 3 times rho times sine phi is equal to square root of 4 minus rho squared sine squared phi. Get rid of this root here, get rid of the root, so square both sides. We get 3 rho squared sine squared phi is equal to 4 minus rho squared sine squared phi. And then isolate for what you need to isolate, bring this term on the other side of the equation. 3 rho squared sine squared phi plus rho squared sine squared phi is 4 rho squared sine squared phi is equal to 4, or rho squared sine squared phi is equal to 1. Now rho and sine of phi, look at this, sine of phi, we are talking about an angle in the first, in this region here, right? Sine of phi is positive. So you can take the square root on both sides and you will get rho sine phi is equal to 1. Well, how much is rho at this point? How much is rho at this point? Rho at this point is 2, so sine of phi is equal to 1/2. Well, finally, phi is equal to arc sine of 1/2, or that's how much? Pi over 6. That's pi over 6. Okay? So finally, we have found the bound on phi, that's from 0 to pi over 6. And now the answer is going to be the volume is equal to theta runs from 0 to 2 pi, so from 0 to 2 pi. Phi runs from 0 to pi over 6, and rho runs from 0 to 2. Of course, don't forget the Jacobian, rho squared sine of phi. This is your answer. Any questions?
Yeah, so would you say it's easier to do like this problem in spherical coordinates? Because I think when we did it in like normal coordinates, you had to do like one volume minus another.
Absolutely, yeah. This is way easier in spherical. The question is whether it's easier in cylindrical or not.
Mm-hmm.
Right. So if you're doing this in, and that is actually going to be, now we're going a little bit ahead of time. It is an art, or let's say with practice you'll figure out what it would be the easiest triple integral to use in a particular problem here. But if you look at if you look in cylindrical coordinates, then you have to find the equation of this circle. I'm talking about cylindrical coordinates, right? This circle. So because that circle here, the projection of that circle will give you the R. What is R bounded by? So you have to find this intersection, okay? And then Z is gonna run from here to here. Now, do you want to find integrals of square roots? I don't think so. Although this square root in cylindrical coordinates is just going to be r squared, right? And this is going to be square root of 4 minus r squared, but yet the square root of 4 minus r squared, an integral of that requires to use help me here, trigonometric substitution. Okay, and then in spherical coordinates, maybe it was difficult to find the bound, but once you found the bound, this is a joke, right? This is that none of them are independent of each other, so it's a you can do this in Cal 1 if I just tell you the procedure how to do it. Okay.
Thank you.
So literally the same question. Okay, I'll do it example 2, and I'll let you guys. The same question can be asked in the following way. Set up the triple integral. Okay, for the solid, for the volume, of the solid bounded above by rho is equal to 2. And at this point, you should know what rho is equal to a constant looks like. Rho is equal to 2. So it's a sphere centered at the origin with radius 2, right? And bounded below by phi is equal to pi over 3. So literally is the same question, except that now these solids are defined in spherical coordinates, because phi is equal to a constant a constant between 0 and pi over 2. That's a cone opening upward, right? So if it's easy for you to recognize this, then this problem is way easier than the previous one, although it's the same geometrical figure. So pi over 3 is, where is it? Pi over 6, pi over 3. So like this, and then above that we have the sphere, right? So obviously this angle here, we go around the z-axis full circle. So theta is from 0 to pi. Rho is already defined from 0 to 2, and then phi also is defined from 0 to pi over 3. So the volume is equal to the triple integral of rho squared sine phi 0 d phi d theta. Theta is from 0 to 2 pi. Phi is from 0 to pi over 3. And then rho is from 0 to 2. Questions? There are no questions. Let's do something slightly more challenging. So here we're going to do changing the order of integration. By the Fubini's theorem, we know that we can flip this integral, right? Should be the same as let's say d theta, d phi, d rho, right? And we have 6 possibilities in the triple integrals, right? Of course, what is going to change? Well, the bounds are going to change, okay? So depending on the problem, right? That problem can be more or less challenging. For example, in our first example that we did, in this example right here, because none of the variables dependent on each other, that's not a problem. You can simply flip this as you want. The theta, but then theta starts from 0 to 2 pi, then the rho, the second one, goes from 0 to 1, then the phi from 0 to pi over 2. So for such an easy problem, that's a no-brainer. That's straightforward. But let's see this example that requires a lot of thinking, well, some thinking, okay? Let E be the region bounded below by the cone z is equal to square root of x squared plus y squared, and above by the sphere z is equal to x squared plus y squared plus z squared. Okay, set up the integral. Set up the integral in spherical coordinates for the volume of the solid, using the following order of integration. In part A, d rho, d phi, d theta. In part B, d phi, d rho, d theta. Okay. This is an artificial way of asking you this problem. Okay, I doubt that you will see a problem like this being asked throughout your education. It has a very good learning quality, because you will see how one setup is way more difficult than the other one. Okay, and of course, based on what we know prior from just Cal 2, you'll see how you have to switch, completely change the point of perspective when you're doing this one rather than this one, okay? Okay, first of all, where would be the problem here, right? In the sphere, the problem is in the sphere. Why? Because the sphere is not centered at the origin. So let's first deal with that, okay? Let's figure out where is the sphere centered and what is its radius. So z is equal to x squared plus y squared plus z squared. That 0 is equal to x squared plus y squared plus z squared minus z. I need to complete the square here. So I need to add 1/2 squared, and in order to keep the equation, I need to subtract 1/2 squared. This is really just standard completion of the square. Bring this guy on this side, that becomes positive 1/4 is equal to x squared plus y squared, and then here we complete the square here, plus z minus 1/4 squared. Okay, so what do we get? We get, that's 1/2, I'm sorry, 1/2 squared. We get a sphere centered at 0, 0, 1/2 with radius 1/2. Okay. So this is the center of the sphere. Okay. And then this is just a regular cone, right? So more or less, we're accustomed, this is the third problem that we're doing of similar nature, but yet is very different. Why? You will see in a second, because a rho doesn't stay constant. Okay? So look at this. Here rho is this constant, right? Less than 1. Here rho goes to 1. So basically it increases, right? Depending on how the phi angle opens up. Okay, so let me just, I don't have the, maybe green would be the best color for this, maybe not. Okay. Okay, what is the easiest part here? Well, the easiest part here obviously is just what theta is doing, and theta simply goes from 0 to 2 pi. That's a full circle, right? Okay, and now the question is, what happens to I'm doing part A, what happens to rho and phi? So phi obviously starts at 0. I'm just going to sketch this here again, just for the point of so phi goes from 0 and opens up to here. So the question is how much phi is. Okay, so where are we going to find that? look at the equation of the cone. So the equation of the cone said z is equal to square root of x squared plus y squared. Right? What is z in spherical coordinates? Is rho cosine phi is equal to square root, again the same, let's call it identity, shows up in spherical coordinates, that rho squared sine squared phi. Well, square root of rho squared sine squared is just a rho sine phi, and because rho is not zero here, I get cosine phi is equal to sine phi. Well, this is very simple. Either you can say 1 is equal to sine phi over cosine phi, which is tangent of phi, and from here phi is equal to arctangent of 1, which is pi over 4. That's one way to think about it. Or simply, what would be the angle for which the angle in the range from 0 to pi over 2 gives you the same value for cosine and sine. Well, obviously that's pi over 4. Okay, so I have the bound on phi. Okay, so far theta goes from 0 to 2 pi, phi goes from 0 to pi over 4. The last thing is what? The last thing is to determine what rho does, right? So rho obviously starts at 0, and then as you can see, it changes the value, right? I cannot say that it goes from 0 to some particular constant, because that maximum constant changes here. Okay, so it's bounded by above by what? And here we look at the equation of the sphere. So we had z is equal to x squared plus y squared plus z squared. Z is rho cosine phi, and then what did I say? X squared plus y squared plus z squared, right? It's very good if you know, if you have an expression for that, that's just rho squared. X squared plus y squared plus z squared is just rho squared. So that's just rho squared, okay? Well, here rho is not 0 from here anywhere up to here, so you cancel those, and you can cosine of phi is equal to rho. So as you can see here on this bound, right, rho above is bounded by cosine of phi, by cosine of phi. So the answer in part A is that if you want to use the order of integration d rho, d phi, d theta, okay, the Jacobian is rho squared sine phi, okay? So rho runs from where? From 0 to cosine phi. Theta runs from 0 to pi over 4. That's phi, sorry. And theta runs from 0 to 2 pi. Any questions? If there are no questions, let us look what happens if we are taking the other. So in part B, I want the volume to be evaluated as rho squared sine of phi d phi d rho d theta. So in a certain way, phi I'm expecting to be a function of rho. Okay, so just to have this picture in front of us all the time. Doesn't have to be a very precise sketch, but here still a sketch is important. So okay, so things will change depending on what happens to rho. Okay, why? Because rho from here to here I can evaluate it how much it is, and then from that moment on rho becomes here a constant, right? So actually that's not true, sorry, take that back, that was a mistake. So we have that rho is equal to cosine of phi, and then I have that phi was equal to pi over 4, right? From here, rho is equal to square root of 2 over 2. Any questions? Right? From the sphere, we have rho is equal to cosine of phi, right? And phi is equal to pi over 4. Phi is equal to pi over 4. That's where they meet, right? So rho is equal to square root of 2 over 2. So as you can see, depending on rho, if rho is between 0 and square root of 2 over 2, okay, I'll have one expression, one relationship between rho and phi. If rho is between square root of 2 over 2 and 1, that means from here to 1, here at most rho is 1, I'll have another dependency on rho and phi. Okay. So first of all, so basically, how am I I'm splitting this? I'm splitting this, finding the volume of the cone only here. How much is the cone? So how much is the volume of this cone? And I'll call that volume cone, plus the volume of the sphere, but only on this part. Only on this part right here. Right? So if I just look at the cone, which means rho is from 0 to square root of 2 over 2, okay? Here, phi goes from 0 to pi over 4, okay? That's easy. And then theta goes from 0 to 2 pi. That's straightforward, right? Theta is going to be the same here also. So the volume of the cone is just the triple integral of rho squared sine phi. Now keep the order of integration that was asked for. D phi, d rho, d theta. D phi goes from 0 to pi over 4. d rho goes from 0 to square root of 2 over 2. D theta goes from 0 to 2 pi.
Evo,
Yeah.
wouldn't phi go from pi over 4 to pi over 2?
Pi over 4 to pi over 2. No, why? How in this cone right here, if you're describing this cone,
Mm-hmm.
how where pi goes
Okay.
from here to here, right?
Yeah, okay.
Okay. So this
I
is
get it.
only for the cone that is a bill, so only for this volume, right? That I just sketched. And then above that, I need to find the volume of this segment of the sphere, right?
Okay.
Of the sphere. The ice cream itself, right? This is the cone and this is the ice cream.
Mm-hmm.
Okay, so on that part, rho is between square root of 2 over 2 and 1. Okay, and then how am I going to bound phi? Well, from the equation of the sphere, because I'm talking about the sphere. So what is the relation between rho and phi? It's right here. Rho is cosine of phi, which means that the phi starts at 0, right? Phi starts at 0, and it goes to where? To arc cosine of rho. Okay, and then theta goes from 0 to 2 pi. So the volume of this part of the sphere is equal to the triple integral rho squared sine phi d rho d theta, where theta goes from 0 to 2 pi. Rho goes from square root of 2 over 2 to 1, and phi goes from 0 to arc cosine of rho. Now, of course, and then the final volume is this integral plus this triple integral, okay? Now, of course, this is way more complicated than this simple integral right here. As again, I said, nobody's going to ask you an exercise like this, not that I know of, okay? But the question, the idea of this question is just how we have to change the order of perspective in triple integrals, right? So changing the order of integration causes a lot of problems, okay? It's not as easy as double integrals, okay? So you have to be careful about that. Any questions?
Evo, I don't get why it's the first thing in the sum is like the area of the cone, because if rho goes from 0 to root 2 over 2, wouldn't that mean it's like already an ice cream cone? Like it's not like a flat cone. That's what I don't get.
I say it again, sorry?
So like let's say for the first part of the sum.
This one here.
Yeah. Rho goes from 0 to root 2 over 2, right?
Mm-hmm.
So that means that the volume would be like an ice cream cone. It's not just like a flat cone with like a flat top. It's like rounded on the top. No? Yeah, wouldn't it be like that?
I think it is, but the actual like ice cream part is also indented because the rho value starts at root 2 over 2. The bottom of the ice cream cone isn't flat either. Like they're both indented that much.
Oh, okay.
This and then
Okay, yeah. Thanks, Colton.
this one. What, Colton?
Well, because I was saying since the rho value of like the actual like ice cream starts at the root 2 over 2, they're both like indented or like curved a bit. Like the ice cream cone
One.
looks
Yeah,
like
yeah,
that,
yeah. Okay,
and then like the ice cream is just like on top.
that's it. Exactly. Is it okay, Charles?
Yeah. Yeah, I get it. Thanks, Colton. Thanks, Evo.
Well, thanks, Colton. The value of this interval is pi over 8 if you want to practice and evaluate it. You should do it, actually. It's a good idea to do it. Here you'll have cosine cubed of phi times sine of phi, and then you'll have to use substitution, and this as an exercise is pi over 8. Now 10. Okay, how much this is done? Okay, converting from rectangular to spherical. Triple integrals, right? So here I want to okay, and the interval is from 0 to 3 dy from 0 to square root of 9 minus y squared dx, and from square root of x squared plus y squared, again the same thing, above the cone, below the sphere dz. Okay, but now here be careful, the integrand, so the integrand is x squared plus y squared plus z squared dz dx dy. So let's see how we're going to do this. Okay, so z is between x squared plus y squared and below 18 minus x squared minus y squared. This will give you the bound of r and phi. This is where we're going to look for them. Okay, but now be careful here. X is between 0 and square root of 9 minus y squared, and y is between 0 and 3. So one thing that we didn't, all the problems involved up until now were what? Were theta went from 0 to 2 pi. We didn't really care about theta. But let's just concentrate on the xy plane before we go into 3 dimensions, xy, right? So this equation here, x is equal to square root of 9 minus y squared, is what? A semicircle to the right of the y plane, the axis, sorry, right? Because x takes on only positive values. If this was plus or minus, then I would have the whole circle, right? Because it's only plus, I get only this circle. Sorry, semicircle. And then this extra condition that says bound the y only for the values from 0 to 3. So basically in the xy plane, we're talking about the first quadrant, because z is bounded by positive values only, and taking into consideration that in xy plane we're talking about the first quadrant, that means that we only work for this problem in the first octant, right? So we're integrating above this quarter of a circle, okay, which right away gives me the boundary of theta from 0 to pi over 2. Okay. The rest of it is common to the previous examples. This is going to be the cone, right? And this is going to be the sphere centered at the origin with radius, how much? With radius square root of 18, right? And square root of 18 is what? Square root of 3 square root of 2. Okay, so I have something like this. So right, there's going to be this ice cream cone right here. But only in the first octant. That's being already dealt, we've already dealt with it because I'm integrating from 0 to pi over 2 in terms of theta. The rest of it is bounding rho above, because obviously starts from 0, and then bounding theta above, because, sorry, phi, because again, it starts from 0, and then what is the bound, right? Both of these, we look them from these two equations, okay? So z is equal to square root of x squared plus y squared. This is an exercise that we have already done. Z is rho cosine phi, which is square root of x squared plus y squared, is rho squared sine squared phi. This is rho cosine phi is equal to rho sine phi. Cancel rho, obviously phi. The angle where cosine and sine functions are the same is pi over 4. So phi is bounded above by pi over 4. And then rho z is equal to square root of 18 minus x squared plus y squared. Rho cosine phi is equal to square root of 18 minus rho squared sine squared phi. Square both sides. Rho squared cosine squared phi is equal to 18 minus rho squared sine squared phi. Bring this on this side and factor rho squared. Cosine squared phi plus sine squared phi is equal to 18. Obviously, rho is square root of 18, or that's, help me here, 3 square root of 2. So rho is bounded above by 3 square root of 2. And then this integral is just this integral right here. I'm just going to write it down because it's very messy here. So the integral from 0 to 3, from 0 to square root of 9 minus y squared, from square root of x squared plus y squared to square root of 18 minus x squared minus y squared, x squared plus y squared plus z squared, dz dx dy, so this is what we started with, is equal to the triple integral. Theta goes from 0 to pi over 2 d theta. Phi goes from 0 to pi over 4 d phi. Oops, sorry. And rho goes from 0 to 3 square root of 2 d rho times the Jacobian, rho squared sine of phi times the integrand itself. But the integrand itself, we already talked about this, right? We already developed or expressed how much is x squared plus y squared plus z squared in spherical coordinates. That's rho squared times rho squared. So of course this can be written as rho to the power of 4 sine of phi And of course, this integral is way easier to evaluate than this integral here above. Again, because of the square roots. Any questions? I'm sorry that I'm coughing in the camera, but at least it's in the camera and not in your face, right? I cannot, this cough hasn't left me for many weeks. I don't know what's wrong with me. Okay, let's do one more problem and that's enough for today. I'll meet you on Wednesday, and on Wednesday we'll do more problems. This is it, that's the material for this semester, okay? So from now on, it's just practicing problems. So the last example, set up the integral for the volume of the region, three-dimensional region, inside x squared plus y squared plus z squared is equal to 4. Okay, sphere with radius to center at the origin. And outside the cylinder, x squared plus y squared is equal to 1 in a rectangular integral, b rectangular coordinates, cylindrical coordinates, and c spherical coordinates. Okay, so basically this means to flip or change between all the triple intervals that we learned. Okay, so let's see what are we talking about. So I have a sphere with radius 2. Okay. Then inside I have a cylinder with radius 1. Okay, so the solid whose volume I'm looking for is this one right here. And then this goes around, right? Okay, and this is here, open. So basically inside there's nothing inside, right? It's empty inside. It's like you have a ball and then you just drill to this sphere, right? So in part A, all the volumes I'm going to evaluate them as the volume the volume above the xy plane, because the symmetry is obvious. Okay, so in rectangular coordinates, z goes from 0, so in rectangular coordinates z goes from 0 to its upper bound is what? Its upper bound is the sphere. From here, how much is z? That's square root of 4 minus x squared minus y squared. Okay, in order to find the bound for x and y, we'll look at the projection of the sphere onto the xy plane, and this is the volume of this washer, right? Not the volume, sorry, the area of this washer. So this is from -2 to 2, and here this is 1 and -1. Okay. So now it's up to you. Which one are you going to take? You can say that y goes from here, right? Goes from a negative square root of 1 minus x squared to 1 minus x squared. And then x simply goes from 1 to 2, from 1 to 2. And that gives you the volume of this solid in rectangular coordinates, okay? So x goes from 1 to 2. So at the end, you have to evaluate the x. Then y goes from negative square root of 1 minus x squared to square root of 1 minus x squared dy. And finally, z goes from 0 to square root of 4 minus x squared minus y squared dz. When I'm evaluating the volume, then here I have 1. Any questions?
Why did you multiply by 2 in the beginning?
Because otherwise I should have taken here from negative. So basically it's 2 times this volume right here above the xy plane.
Okay, thank you.
If I didn't multiply by 2, then here I should have taken minus 4 minus x squared minus y squared. Sorry, y squared. And then I wouldn't have done this. Okay? So let's see what we have done here. Let's see if this is correct. So because this, what this gives me is nothing else but, yeah, this is good, right?
I feel like there's some values of x missing. Because like if it goes from 1 and 2, that means like your y value associated to your x can only be between like 1 and 2, right? Like wouldn't it be the like
Y is from 0.
because their x
Just
can
give me a
be
second. You're right. Just give me a second.
okay.
No, this is not good.
Wouldn't x be between 0 and 2, and then you do like y is like square root of 1 minus square root of 2 minus x squared minus square root of 1 minus
Man,
x squared?
I can't. I'm not concentrating on what you're saying. Just give me a second here, okay? Most probably you're
Sorry.
just give me. This is nonsense, right? This cannot be when x is equal to 2. This doesn't work. I get negative under the root, so this is not good. Okay, go now. I'm concentrating on you.
So what if we make x equal from 0 to 2, and then we make y equal like the greater circle minus the smaller circle? Like it's between the greater circle and above the smaller circle.
Yeah, that's it. So you know what? Let's find the volume of the sphere. So let's find the volume of the sphere. This is not good. The volume of the sphere is going to be like this, right? So 2 times x goes from 0 to 2, right? And then y goes from 4 minus x squared to this. This is the volume of the sphere. That is correct, right?
Yes, that is
Only
correct.
of the sphere. Minus the volume of the cylinder. That would work. Minus 2 times Okay, now here, how much is Z? From 0 to this point right here. So let's find that point where these two meet, right? So x squared plus y squared is equal to 1, and x squared plus y squared plus z squared is equal to 4. If you put them together, you get x squared plus y squared is 1 is equal to z squared, sorry, plus z squared is equal to 4. So z squared is equal to 3, z is equal to square root of 3. So now I'm talking about the volume of the cylinder. So it goes from 0 to square root of 3. And now the shade of the cylinder in the xy plane is right here from -1 to 1. So y goes from, if x goes from -1 to 1, and then y goes from square root of 1 minus x squared to 1 minus square root of x minus x squared. And then here, dz, dy, dx. All right, this is it. This is the answer. Is it good? So basically, volume of the sphere minus the volume of the cylinder. Any questions? No questions?
But if you remove like the volume of the cylinder, there's still like the cap above the cylinder and under the cylinder that you like didn't account for, no? So like, wouldn't Z's maximum value be like where they meet?
Yes, and that's square root of 3, which we evaluated
So
here.
then in your first
It's not,
integral,
it's not 2, it's square root of 3, it's not 2, right?
Yeah, exactly.
So Z
So in your,
up to here. And
yeah,
that's the most Z that I want to figure out. How much is the volume of the cylinder right here? If this
the
is,
volume of the cylinder is good, I think.
huh?
I think the volume of the cylinder is good, but I wasn't sure if you were including the cap.
No, you're not including the cap. The cap of the sphere, no.
Okay.
Huh? 5 more minutes, okay? So 13.
I have a question.
Uh-huh.
When you for the volume of the sphere, when you let x go from 0 to 2, isn't that only taking
Negative 2 to 2.
Okay.
Thank you very much. Very good, thank you. Okay, so now cylindrical coordinates. Okay, while cylinder is involved, somehow it tells me that cylindrical coordinate should be the easiest one. Okay, maybe not. And why is that so? Because the projection onto the xy plane is very simple to describe, right? This area of this washer here in the xy plane is easily described as theta goes from 0 to 2 pi, and then r goes from 1 to 2. Very simple, right? And then z is between 0 and, well, the sphere here. And the sphere is square root of 4 minus x squared minus y squared, sorry, plus. So that means z is between 0 and 4 minus r squared. So in cylindrical coordinates, the volume is 2 times, again, I'm taking 2y because I'm starting at 0. Okay, theta goes from 0 to 2 pi. Am I here? Yes, you see me? Yes. That's the theta. R goes from 1 to 2. That's the R. Z goes from 0 to square root of 4 minus R squared dz. Right? Don't forget the Jacobian of the triple integral in cylindrical coordinates is R, so don't forget that guy right here. And the last part is how to express this in spherical. Well, for about the spherical coordinates, all I know for now is that theta goes from 0 to 2 pi, right? And now let's look at this intersection here, sorry, cross section. So this is 1, the cylinder, and this here it's 2. Okay. So first of all, let's talk about phi. Phi starts from here. Like if I'm about to describe this part only, right? So that comes from so this outside is the area that I want to whose volume I'm looking for. So how do we describe that area? The angle starts from here and it goes to pi over 2, right? So phi is bounded above by pi over 2, but where does it start? How much is this? How much is this point right here? Okay, so how are we going to find that? Well, I'm going to look at the, where was my question? So where these two equations meet, right? So I have x squared plus y squared plus z squared is equal to 4, and x squared plus y squared is equal to 1. From here, z squared plus 1 is equal to 4, or z squared is equal to 3, right? From here, z is equal to square root of 3. And what does z stand for? Stands for rho times cosine of phi is equal to square root of 3. Okay? Well, how much is rho right here? Right? What is rho right here? This is the value of rho, right? This is the value of rho, which is given by what? Is given by the cylinder, right? So we have x squared plus y squared is equal to 1. This expression x squared plus y squared always coming back, that's rho squared sine squared phi is equal to 1, right? Or from here, rho squared is equal to 1 over sine squared phi, which is cosecant squared of phi. Take square root on both sides, you have rho is equal to cosecant of phi. Okay? But from this equation here, what do we have? We have that rho, second, that rho squared is equal to 4, which implies that rho is equal to 2. Okay? So if you come back here, you have that cosine of phi is equal to square root of 3 over 2, and that implies that phi is equal to pi over 6. That's true. So phi starts at pi over 6 and then finishes at pi over 2. And from here, this expression gives you the bound on rho. Rho is going to be, it's bounded by, so it starts from here, right? This is how much the radius is. Starts from the cylinder, goes to the sphere. Starts from the cylinder, goes to the sphere. So the upper bound of rho is the radius of the sphere, that's 2, right? But the lower bound comes from the cylinder, that's cosecant of phi. Okay, and this volume is equal to 2 times the triple integral. Theta goes from 0 to 2 pi, the theta. Phi goes from pi over 6 to pi over 2. And rho goes from cosecant phi to 2. Don't forget the Jacobian, rho squared sine of phi. Any questions? Okay, if there are no questions, I will upload this video and the previous video of cylindrical coordinates of the previous class today alongside the notes from Frank Lovasco and